Welcome to Brain Vision.
Here we can say that we're going to choose a differential area equaling dx times dy. And this would essentially divide the plate up into differential rectangular elements, where each element has a differential area. So we can say that the mass of an element, dm, would be equaling m over the length times the width multiplied by dx dy. The distance of that element from the axis of rotation r, we can say is equaling the square root of x squared plus y squared. And we're going to then use equation 1016 to calculate the moment of inertia. So we can say that the moment of inertia of the center would be equaling square root of r squared times dm. This would essentially be equaling the integral from negative width over 2 to the width over 2 times the integral from the negative negative length over 2 to the length over 2 multiplied by x squared plus y squared multiplied by m over the length times the width times dx dy. And so we can then say that the moment of inertia through the center would be equaling 4m over the length times the width times 0 to the width over 2 times the integral from 0 to the length over 2 times x squared plus y squared times dx dy. This would essentially, we can solve one part and say that here the moment of inertia, rather we can just say this would be equal to 4m over lw times the integral from 0 to the width over 2 multiplied by 1/3 times 1/2 of the length, or we can say 1/3 times the length over 2 quantity cubed plus 1/2, or rather we can say the length over 2 times y squared times dy. And so the moment of inertia through the center would be equaling 2 times m over w times the integral from 0 to the width over 2 multiplied by L squared over 12 plus y squared times dy, and this is going to be equaling 2m over w times L squared over 12 multiplied by the width over 2 plus 1/3 times the width over 2 rather, quantity cubed. And we finally find that the moment of inertia through the center was equaling m over 12 multiplied by the length squared plus the width squared. And so this would be our final answer for part A. And then for part B, we essentially have here, for the axis of rotation parallel to the width dimension, essentially the rotation axis would be in the y direction, we can consider the plate to be made out of a large number of thin rods. Each rod has its length L, and it's rotating about an axis through its center. So we can say that the moment of inertia of one rod would be equaling 1/12 m sub I L squared, and m sub I would be the mass of one single rod. So for a collection of these rods, we can say that the moment of inertia with the rotation axis being in the y direction, this would be equaling the sum starting at I of 1/12 m initial L squared, and this is simply equaling 1/12 times the total mass m times L squared. Similarly, if the axis of rotation was rather in the x-axis, I sub x, this would be equaling 1/12 times the total mass of the collection of rods, but now instead of the length squared, this would be the width squared. And this essentially proves the perpendicular axis theorem. So with this combined with this is essentially proving equation 1018, where the moment of inertia through the z-axis would be equaling the moment of inertia through the x plus the moment of inertia through the y. And that's essentially what we calculated here. That would be our answer for part B. That is the end of the solution. Thank you for watching.